stay the same. When that energy is available, things will move. Things will change. You have to understand that. Somebody telling me that they're monatomic minerals. Oh, no, they're not monatomic. They're in the Ormus state. What does that mean? Well, they're single atoms with a deuterium attached. Said, don't run that by me. I've worked too long with nuclear engineering, and I've worked with people who do the same thing my ex-partner did. And they know as soon as you add energy, it's gone. It changes. You don't add deuterium to an atom and expect it to remain as we're going to have a change there. Atoms like to cluster.
So it's not monatomic, you're saying?
No, I've never found any one of those products to truly contain monatomic elements. And neither have the people that work with metallurgy. No.
Right. So what is their state then? The so-called Ormus or monatomic elements?
Well, first of all, you got to show me a monatomic element.
Well,
now I am privy to some inside information. A man went to see this powerful healer in India named Sai Baba.
Yeah. Sure.
Well, Sai Baba makes the stuff in his hand that pours out called Djibouti. We've analyzed Djibouti. Djibouti is element 61. It's promethium. And it wasn't discovered in the crust of the earth until very recently. And technetium, element 43, has never been discovered anywhere in the solar system until I discovered it in a cometary fragment. Now this is what freaks people out. I could feel the energy of this fragment from miles away. I drove straight to it, stopped my truck, got out, and walked straight to it, and buried in the ground with about that much showing above the ground was what looked like a meteorite fragment, all pitted. I dug it out, a chunk about that big, brought it home, and now we believe it was a cometary fragment because it contains a stable isotope of technetium. No such thing is known to exist. I've got one. The energy is in this water. It's a very good modulator for the hypothalamus gland. Check that out thoroughly. I can't tell you how many hours and hours and hours and days and weeks and months went into developing this water. It's an unbelievable story. It would take quite a huge book to unravel the whole thing. But the point is, the same partner who succeeded in making the gold nuggets had a heart attack. So he goes in and one coronary artery is kinked. So they slip. They didn't know if this would work. They slipped in a stent, expanded it, worked. Oh, the guy said, Dan, I should have known there was something wrong. He said, I would climb a little flight of stairs, and when I got to the top, I'd be out of breath, exhausted. I had to sit down and rest. He said, I was tired all the time. I couldn't stay awake. He said, when they opened up that coronary artery, I felt like a new human being. And he's in his mid-60s when this happens. About 12 months goes by, and he feels lousy again. He goes in, and they put 3 more stents in. Now he's got 4 stents. Feeling really good for 9 months. Everything goes to pieces again. Goes into the doctor. Well, either more stents or bypass surgery. My partner says, this is like everything else, isn't it? It's a Band-Aid approach. This doesn't solve the problem. It does not stop the accumulation of plaque. We don't know how to do that. Okay, he says, let me think about this. He goes away, gets in touch with his friend who's a nuclear engineer, and they go to work on the problem. They find out that the plaque in his coronary arteries is aluminum phosphate. If you view the brain of someone with Alzheimer's, there's a plaque in the brain, aluminum phosphate. Carotid arteries, aluminum phosphate. Below the heart, rarely ever aluminum phosphate, calcium phosphate line. So they figured out if they took isotope 125, now, let me back up. Let me tell you a brief story. One time, my partner sent a bottle of water to an elderly woman in her 80s. He got a phone call from her son who just chewed his butt out. How dare you take advantage of my mother? She's in her 80s. What's wrong with you? I'm the professor at chemistry at a major university, and these isotopes don't exist. Well, first of all, my partner said, well, I'm sorry. I'll refund every dime, the postage, the cost of the water, everything. Will that satisfy you? Yes, it will. And then my partner, before he had a chance to say anything else, said, by the way, teaching chemistry in college, you'll never run into these isotopes. They are all out of the publications of the U.S. Atomic Energy Commission. And I'll give you the numbers of the publications. You can go look them up yourself. Oh, the guy changed his tune. He said, really? Yes. You never deal with these isotopes. They're very unstable. You can't keep them around, but you can keep them around as their energy that is frequency analog in water. You can keep them around indefinitely in water as the frequency analog. Why not? That's not unstable if you know how to do it. Okay, now, after that he said, you know what? If the body needs isotope 125 of indium, what else does it need? They got to looking into it, and all the mineral supplements you buy in the health food store are absolutely wrong. Your body can't even begin to utilize those minerals. They're not the right isotope. They're the wrong form of that element. The correct form is an unstable isotope. And the correct state is not in the atomic or molecular state. The correct state is as energy in water. The world's ultimate mineral supplement is sitting right here in front of you tonight in this bottle. There's about 42 to 43 elements from the periodic table in here as their mathematical analog. It does a beautiful job of mineralizing the body. Cells, ask a biochemist. A cell has no provision for dealing with minerals in a solid state. They're just more garbage and debris. Why would a cell take something that's bigger than a nanometer when it can't get it through the receptor site anyway, because no receptor site is bigger than a nanometer? How is it going to get it inside the cell? And if it did, what's it going to do with it? What is it going to attach it to? What's it going to fix it to? Yes?
How did we get into this predicament evolutionarily in which we don't have the nutrients in our environment that we need, that has to be manufactured in a laboratory?
Well, I've got some theories about how things were different on the planet some years ago. And it all deals with thermodynamics. There's been a real shift in thermodynamics on the planet. And for that reason, water changed, and this whole process became somehow interrupted and distorted. Yes?
Well, you were speaking of the river and the gold deposits. Couldn't that partly be due to pollution concerns, et cetera? We're no longer just drinking running water in streams. We're drinking purified, chlorinated, whatever water. We're not just going up and drinking all this pure water that may have the energy in it from natural processes.
Well, there are no natural sources that contain this energy. None. None that we know of. There may be. We've never found one. But I had a man come to see me 2 summers ago from Sydney, Australia. And he's devoted his life to studying water. But his passion is cleaning up groundwater. And they have these really funny looking cages based on geometry. They're made of plastic. And they build a trap where the groundwater flows into these, and it regenerates, it re-energizes the groundwater, and the water becomes self-cleaning. Self-cleaning when it's energized. Now, we both agreed, here's what de-energizes water the most, is forcing it through laminar flow, through pipelines. That kills water. Because water, by its very nature, wants to move in a vortex configuration and tumble. It never stops moving. Water molecules, unlike the conventional model of physics, are not like the molecules and atoms in the air that are bumping into one another. Okay? Yeah, we see what we call Brownian motion, but what's happening to those things is we need to observe Brownian motion a little closer, because there's a pattern to the movement of water. There's a definite pattern to the movement of water. Because water isn't made up of simple H2O molecules. There's a good reason for that. Water, although H2O molecules are involved, here's the problem. When we have water, we have the oxygen here. That stands for oxygen, and we have a hydrogen over here. And we're going to put the hydrogen right here. We're going to put another hydrogen over here. Okay? Now, essentially, they're in an electron sharing and pairing arrangement. So here you've got just one proton, unless it's deuterium, you've got a proton and a neutron, and instead of H2O, they call it D2O, okay? But in this case, the oxygen with all the electrons ends up with the net negative charge, and this end of the molecule ends up with a net positive charge because these protons have a positive charge. So now it has what we call in physics a permanent dipole moment. It's like a magnet. And water has an irresistible tendency to get involved with other water molecules, so it'll form structures. So this is a kind of crude, but bear with me. Let's say I've got some Velcro on these. Make sure I get the right ones. Okay. That's stuck together. And let's see. Where's this one? Oh, it came apart already. Well, it's not sticking very well. Okay. Anyway, what happens is this. Let's imagine this is a water molecule. Let's say that the yellow at the top represents the oxygen. The purple and the red represent two hydrogens. Okay. But now we're going to all of a sudden turn these from atoms into molecules. This is an entire water molecule, so is this, so is this. So what will happen is now they'll come together, and the simplest configuration would be something like this. Now I put two pins in here to represent the two hydrogen protons, okay? And this is what your water particle is going to look like. The simplest one is going to be based on a tetrahedron. Nature abhors a couple of things. One is instability, and the other is asymmetry. It loves symmetry. In physics, we're always looking for symmetry. But for some reason, we assume, oh, water's perfectly fine in an asymmetrical state. No, it's not. It's going to form three-dimensional structures we call polyhedra. The next one is a cube. So we put four like this. Let's imagine we had four more stacked on top of these. But they wouldn't be stacked here, here, and here. They would fall in between the gaps, here, 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 and here. It's like you took half of this cube and twisted it 90 degrees. Then the next bigger polyhedron is a little more complicated. It's called a dodecahedron. But here's the interesting thing. I found in my work that the water molecules, for the most part, were coming together and forming huge structures, about 1,000 times bigger than can ever pass through this little active protein channel on the membrane wall of a cell called an aquaporin. See, a guy was awarded a Nobel Prize for discovering the aquaporin. It's an active protein channel. This looks like a little funnel. And only one water particle at a time can drop through the funnel into the cell. Only one is permitted. It's called an aquaporin. And the biggest particle that can get through an aquaporin is about a nanometer, a billionth of a meter. 1/1,000,000,000th of a meter stick. Divide a meter stick into a billion parts, and that's the largest particle that can get through the membrane wall of the cell. And most of the water particles, 95 to 98% of all the water you're trying to drink is made up of micron-sized particles. They're just huge. That's what happens when we take the energy from water. It's a form of thermodynamics that has nothing to do with kinetics, nothing whatsoever to do with motion. It has to do with something else. And it's going to get us back to this. I never leave things entirely dangling. I'm going to go back to this. How could you engineer water? Very simple. Normally, the angle from this proton to this nucleus to this proton is about 104.5 degrees. Okay? 104.5 degrees. Now, it's this angle, actually, let's say that the ideal ground state of a water molecule, unattached to anything else, would be 104.5 degrees. But when they're locked into even the smallest structure, the bonding angle goes quite large, up to 122 degrees. But in the big micron-sized particle, it's somewhere about 109 degrees. Okay? So I had to figure out, how do I change the bonding angle? To get the water, as soon as you change the bonding angle, the size and configuration of the particle has to immediately shift. And you do that by charging the protons of the hydrogen atoms. You're going to change the protons, and we're going to put them into what we call a higher spin state. We're not going to change the spin integer because spin is a quantum mechanical effect. And in reality, what it means is that every particle of mass in the universe is like a little engine engaged with vacuum space. I'm going to change the index of engagement with that particle in vacuum space. And I'm going to pull energy into the proton, and as soon as I do, what's keeping them at this angle is this a little electrostatic field around them, the positive charge. And they're pushing on one another. They'll only get so close, and yet, according to the laws of quantum mechanics, they don't want to get too far. Unless I change the strength of the electrostatic field, they'll push away from one another and they'll form a bigger angle. And I've got them out to 122 degrees from one another. Oxygen, proton, proton. 122 degrees. When that happens, we get the smallest possible water particle. And it's actually sub-nanometer in size. We get particles that are not only 1,000 times smaller than the micron, down to a nanometer. They go on down to less than half a nanometer, down into the what we call the angstrom range. That's why when this water that I engineer was analyzed this summer, I can't mention this man's name, but there's a gentleman who, Steven Spielberg, actually made a movie about something that happened to him and his girlfriend. And everybody loves this movie, and they think it's great science fiction. Science fiction, my eye. It's a true story, people. It actually happened. People don't realize it. They tried to kill him and his girlfriend because he was involved in producing a workable hydrogen cell. And somebody doesn't want that cheap energy on the market. They control you and I by making us dependent on what we think only they can supply energy. And that's an illusion. A carefully created, contrived illusion, okay? But here's the story. This gentleman found out about my water. Calls me and he says, no, I'm a physicist. I'm a scientist. I can't take your word for it. I need documentation. I said, my friend, the documentation is waiting to be done. You got any ideas? Well, he said, because of the exposure I've had in the past, I don't want a bunch of fanfare and I don't want a bunch of attention drawn to me. So he said, here's the deal. We found a graduate student at a very obscure college and she needs some credit. So she talked her professor into giving up a whole Saturday and coming in to test my water. So a couple came from Singapore for this test. This physicist and his girlfriend, who's a brilliant German chemist, they came. Another couple came from another town, and then they had a bunch of graduate students there. They call me on a Saturday morning, and the professor of microbiology says, what should we do to test your water? I said, well, we can't photograph water under what we call an atomic force microscope. Because in a vacuum state, water won't stand still for a photograph. It's got to be done in a vacuum condition. And water is just going to move off. You can only photograph a molecule or an atom in a solid, but you can't do water yet. So we can't really photograph the water particle, and we can't compare my water to other waters. I said, how about permeation tests, membrane permeation tests? Oh, he said, that's a good one. What we'll do is use cells. Isn't that the ultimate test, the cell itself? So they used plant cells. And the plant cells are prepared by dehydrating them with salt. And it's called a standard absorption test. And everybody in biology does a standard absorption test. And the physicist looks at the professor of microbiology and says, what are we looking for? And he says, nothing. Nothing ever happens in a standard absorption test. He says, you'll wait forever. You'll grow old and die looking for those cells to hydrate. It'll take hours for them to start, sometimes days to finish hydrating. Okay, so they had 3 samples of highly purified water. One was reverse osmosis, one was distilled. I don't remember how the third one was prepared. The 4th sample was my water. So they went ahead and took the dehydrated cells. They're under the microscope. Everybody can see them on the monitor. They add the water and they start timers. And they're waiting and waiting and waiting. And finally the physicist says, you know, we're wasting our time. Let's use Dan's water and see what happens. Okay. He puts my water on the slide, hits the timer and stands there, gets this amazed look on his face. He's staring at it. He lunges forward and hits the timer. He says, my God, the water started going in within 10 seconds and finished hydrating in 30 seconds. He said, this is amazing, astonishing. Nobody's ever seen this happen in history. It went through that cell membrane wall like it wasn't there. Oh, you have to do that again. That may have been an anomaly. Well, it happened over and over again. It went through the cell membrane like it wasn't there. So a biochemist in the Midwest said, yeah, but those are plant cells. We need to do it with the kind of cells we're made out of. So he works with a butcher shop, and he went to a butcher shop and got absolutely fresh killed beef, pork, turkey, and chicken. They go home and he has to quick freeze it, and they make thin slices to put on the microscope slides. Then they have a process where it takes, I believe, about 3 to 5 days to dehydrate them with salt. He said, by the way, the first time I called you in the summer of 2004, I knew from reading an interview you did on the internet with some guy that you knew what you were talking about. But he says, I'm like everybody else, I need proof. So he says, here's what happened. I went out and collected 19 supposedly high-tech waters. 19. And mine was number 20. He said, we went ahead and added these waters, and there's a particular dye we put into so we can see where it's going. We put the waters on the slides. Each water went on the 4 tissue types. And we wait, and we wait. It took a minimum of 3 days to see any hydration going on with any of those 19 water samples. Now this guy says to me, I don't want you to get a big head about this, but he says, your water went in and hydrated in 10 minutes. He said, here's what's curious. I took 1/4 of an ounce of every one of those samples and put 1 drop of your water in and let it sit there for a while, redid the test. It cut their hydration time in half. Went to 1.5 days from 3 days. He said, your water changes all these waters. Said it's thermodynamics. And we're not talking about heat transfer, heat flow, kinetics, movement of molecules, atoms, it's something else.
So you mean the frequency state of your water affects the water that it's mixed with?
It sets off like a thermodynamic chain reaction. So when I talk about thermodynamics in my work, I say, okay, you go back to the work of Boltzmann, and you deal with something called the equipetitioning of energy. In other words, we refer to it as thermodynamic equilibrium. Have you ever heard of that expression? Thermodynamic equilibrium. Okay. When a collection of particles reaches thermodynamic equilibrium, it's now in its most probable state. I don't want water in its most probable state. I want it in its least probable state. And that's where I took water. Mathematically, it has to be in its least probable state. Is it stable in its least probable state? Yes, it is, unless the mixing ratio is not favorable. Then the other water will kill its thermodynamic state. Otherwise, it'll take all the water it's mixed with and pull it to a higher thermodynamic state. The other way is to kill it with microwave. It's the only thing I know of wrong frequency, folks. It's killing all the nutrients in your food if you're using one. It's destroying your food. You might just go hungry and not eat that microwave food. I know a gentleman that was involved. He's a graduate of Montana State University, by the way. He was involved in producing or creating the microwave. And a lot of those men, when they found out what the energy was doing to water, they would not use them themselves. They would not use them themselves. Yes. Okay. All right, so anyway, we'll get off.
What does it do to water? What does microwave do to water?
Here's a physics, third-year physics grad. What does it do to water?
Makes it vibrate faster to create heat.
Yeah.
So and what does that do?
When it vibrates that fast,
Yeah.
my particles come apart. It changes the bonding angle.
Uh-huh.
Okay?
But I mean, to regular water,
felt that it was vibrating the particles, was shaking them too much. Yeah, that's what, heat is kinetics.
Yeah,
It's motion.
right.
Yeah. And when they saw how efficiently it heated, they concluded something here isn't right. In other words, scientists have superstitions too. It's, oh, we're putting that water in our bodies. I don't think so.
Wow, okay.
Yes, Stephen.
Getting back to what you said some minutes ago about the spin on the atoms, and does that have anything to do with how Putov's zero-point field? Do you know that?
Yeah.
Is that how the spin fuels itself?
Yep. In fact, all reality comes from this zero-point field. Everything, every particle of mass is a manifestation of the zero-point field. Its existence comes out of it. Its identity, its characteristics, everything comes from the zero-point field. It's just the zero-point field expressing itself in multiple ways. I have problems with the idea of the particle zoo. All the particles we're finding, I think most of them only exist under those special conditions.
Right, they're artifacts, right?
They're artifacts.
Out of creaming them with ridiculous amounts of energy and smashing them into each other.
They're
It's nonsense.
yeah, that doesn't. Yeah, that's right.
It's like you smash a car into a wall and say, oh, that crumpled thing right there, that's part of a car. That's how
Yeah.
a car is made.
That's why this ongoing research is just that. Whatever comes out of that? Some things come. Quantum electrodynamics produced a lot of practical things. But a lot of the other work never produces anything practical. Here's the deal. Einstein gave us a really bad equation. My favorite cartoon is that, remember The Far Side? Yeah. Oh, yeah. You'll like this. Here's the guy with his axe. Remember how that guy used to be dressed? Looked like an old woodsman. He's got his big axe. And he's got this chopping block. In the one frame, on the chopping block is a piece of wood, and it says good physics. In the other frame, on the chopping block, is a model of the atom, and it says bad physics. He's going to split wood or split the atom, see? Okay. In other words, it's hard to say what is good physics and what's bad physics. If we go into the past, we've had to change ideas, we've had to modify ideas, but was the physics they did bad physics? No. But what if nothing practical for you and I ever comes out of that physics? Then do we call that bad physics? I call it sucking down grant money. I call it making a living. But that's, whatever. I wanted to bring something into existence that really benefited the human race. Yes.
I have a different question. What about infrared heating for heating food? Does that change the molecular structure of the food?
Oh, the heat's all about infrared.
So is that
That's how we get particles to jiggle.
Is that okay to use it?
Yeah. When one form of energy impinges on a particle, it's going to create a kind of a reaction. Okay, that's how we get it to move. Okay, it's like Heisenberg's uncertainty principle. We can only analyze a particle using another particle, and that has limitations. That's one of the reasons why the uncertainty principle popped out of everything. I mean, you can't know simultaneously the exact position of a particle and its momentum. It's not allowed by the laws of quantum mechanics. It simply isn't allowed. But there's other reasons for that. It's because we're analyzing one particle using another particle. We're looking at something with a photon, which has a definite energy level. And the energy level needed to examine position is different than the energy level needed to examine momentum. It's got limitations, see? Built-in limitations, yes.
Okay, so we take your water, we get healthy. We don't have heart attacks, we don't have strokes, whatever. Now we're living in this electromagnetic world that's killing us as well.
yeah.
Like you said, 68 hertz. I was, and if it was over 100 hertz, it's okay, but we've got the thing with it
Protection.
all right.
Protection. This is what we're going to talk about tomorrow.
So can you go over about what happens in 60 hertz and 100 hertz and what you said second?
Well, any electromagnetic frequency between 40 and 100 hertz tends to be extremely harmful to biology. And the 60 cycle power grid is a nightmare for us. It's a virtual nightmare.
The one we're surrounded with.
Yes. Yeah, it's not good. Its effects are insidious and slow, but you can't sit there and say that it has no effects. Yes, it does have an effect. I don't care how many years it takes for it to manifest itself. You know, they say before you get cancer, it was in the process of coming on for what, about 20 years? Yeah. Things don't pop out like that. They gradually do. In other words, the equilibrium of your body is interfered with in some way, and the degradation at the molecular atomic level takes a long time to manifest itself. It can be very subtle at first, very subtle, until it reaches a crisis stage. Then it's not subtle. And then you're a basket case on your way to the hospital in an ambulance, see? Stephen.
We've been finding lots of people who've had head injuries in our work, or toxic chemical shock and other kinds of traumas are highly electromagnetically sensitive. And,
Yes.
I'm wondering if you have any insights into that electromagnetic sensitivity?
You know, it's like sensitivities to foods and chemicals. And there's reasons why people end up with heightened sensitivities. And it has something to do with the effect that continual exposure over a long period of time has had on the cellular function. And those sensitivities can be reduced. They can all be reduced. I've taken extreme sensitivities and gave my opinion. If I had your sensitivity, I think this is what I'd do for me. Apparently they decided to try the same thing for themselves, and it worked. That's the way I have to operate to keep out of trouble. I can't tell anybody, here's my recommendation. Here's what I'd do if I was in your shoes. See, I speak from experience. When I go out in front of a group of people, I've had cancer twice, and one of them was incurable. It was pancreatic.
Yourself?
Yes. Gone in just about 3 weeks. That was over 15 years ago. I never had a problem since then. I had a brain tumor. I was going blind in one eye. The tumor was wrapped around the optic nerve, the back. Got rid of it. Went to a doctor in California that had an amazing laser made in Geneva, Switzerland called the 632 soft laser. What made that tumor release from my optic nerve? Frequency. It was an orange laser. Frequency. Ultimately, you're going to find everything I'm involved in is wrapped up in this neat bundle called frequency. Everything's frequency. Everything in the universe oscillates. Here's the deal. Technically speaking, vibration is an intrinsic property. Oscillation is how it interacts with everything around it. Technically, in the most strictest sense, everything has a vibratory frequency. Oscillation is how it interacts with those things around it.
So is oscillation the product of two frequencies coming together?
Well, yeah, it could be. It could be. You know how waves interact and they reinforce and cancel. Yeah.
So is oscillation a variation in amplitude? Is that technically what it is? Or?
Well, it is amplitude. It could be any amplitude. Oscillation could be a very low amplitude, a very high amplitude.
Okay.
Or how the amplitude of two waves maybe averages out. And,
Gotcha.
you know, okay. And, you know, if you have a very short wave and a very long wave, the short wave will go right through the long wave and like it doesn't see it. So, you know, physics is a lot about quantum mechanics is the study of waves. Now, that's my passion is wave mechanics. And the idea here is everything I'm doing is actually done with wave mechanics. And if you come to the seminar tomorrow, I'm going to illustrate something that's just ridiculously simple. But it's number 2 principle that I want to drive home to you. And if you don't understand what I show you first thing tomorrow, you might as well go home and we'll refund your money because you won't understand a seminar. This stuff is very simple. I'm not going to make it any more complex than it has to be. It's not going to be rocket science. It's going to be very simple stuff and easy to apply. Everything I do is incredibly simple to apply. It's all no-brainer stuff. Very, very easy. Is it difficult to drink water? You'd be surprised. For some people it is, because they never drank water. What's that? Is that in coffee? Is that in tea? Is that in pop? Oh, yes, the basis for all those things. But you know what? You ought to try drinking it all by itself. It does something very interesting. It'll get rid of those headaches you're having. Because this thing up here, unlike the rest of the body, is about 90% water. It wants to replace that fluid every day. And as that fluid gets dirtier and dirtier, but the water is so crucial. Consciousness will not occur without water. Trust me. Water and consciousness go hand in hand. The brain, the tissues in the brain will ratchet down on the water to hold on to it. It's called microcellular ratcheting. And it'll create headaches, doozies. The brain is attempting to hold on to the water. It can't operate without water. Interesting fact. Then we'll get to your question. These are, you go into the study of people in the past. You wonder, how do these people know these things? The English word, which relates to the retrieval of information, is memory. But memory is two Hebrew words. It's two Hebrew roots. Mem, water. Ori is light. How in the name of God do those people understand the relationship between consciousness, memory, the capacity for memory or recall of information, and the importance of water and light? To them it was like the reflection of light off the waters of the brain. And in reality, it is that. You cannot interface the information in your memory without water, because the memory is not in the brain. It never was. It never will be. Your brain doesn't store, excuse the expression, but a damn thing. It doesn't. Everything you know is in a field around and through you. It's like a hologram. And the human brain is an access device, people, and a translator. Helps turn that information into microelectric current. The neural network is always changing to accommodate for changes and everything that field experiences. You store it all. It's always being modified by new experiences. It's an energy field. It's like a three-dimensional hologram. And the neural network is just there to accommodate the information in that neural network. Now, a couple of years ago, the American Psychiatric Association in their journal published an article. Fascinating. They were doing experiments with work on near-death experiences. And they found out if the brain shuts down to a certain level, consciousness drifts into the field where it originated in the first place. You have an out-of-body experience because your consciousness is actually the field of consciousness. It's all around you. In fact, on a hot day, this field extends itself. Isn't that interesting? It's temperature sensitive. It has a little thin membrane around it, an energy membrane. And it'll blob here and there. And sometimes as you have energy from the universe impinging on it and charging it, you'll see bubbles come off it and just float away. It's fascinating. Fascinating. But the thing is, that field is steady state. You carry that information until you die. In fact, the accumulation of all the things you've come in contact with your whole life continue to modify that field. And the neural network is there to download it. It's like a modem for a computer. It's access. That's all it is access. It's not storing a thing. Dr. Robert Pribram at Stanford University was onto this. The brain was working as a hologram. Carl, that's right. Carl Pribram. Yes?
In Egypt, the word for brain and the word for mind, one was AIS and the other was SIA.
Okay, teach me. AIS.
And SIA.
SIA.
I don't remember which is which, but they recognized that it was a mechanism for downloading.
Interesting. Fascinating.
Do you remember the figure in Al Capp who has like a little thundercloud around his head, stuff like that?
Yes, they do. Absolutely.